Welcome to this solution breakdown for problem number 1215, stepping numbers. In this session, we'll explore the concept of stepping numbers, discuss potential approaches, and analyze their efficiencies. Let's dive in and see how we can solve this interesting problem. A stepping number is a special type of integer where every pair of adjacent digits has an absolute difference of exactly 1. For example, the number 321 is a stepping number because the difference between 3 and 2 is 1. And the difference between 2 and 1 is also 1. In contrast, 1234 is not a stepping number because the difference between 3 and 4 is not 1. Now, given two integers, low and high, the task is to find and return all stepping numbers within the inclusive range from low to high, sorted in ascending order. For example, if the range is from 0 to 21, the output should include all stepping numbers within that range. The input format consists of two integers, low, which represents the starting point of the range, and high, which represents the end point of the range, both inclusive. The output should be a list of stepping numbers sorted in ascending order. In the first example, when the range is from 0 to 21, the output is a list of stepping numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 21. Here, all single-digit numbers from 0 to 9 are valid stepping numbers because they have no adjacent digits. For two-digit numbers in this range, 10, 12, and 21 are stepping numbers. This is because the absolute difference between the digits in these numbers is exactly 1. For example, in 10, the difference between 1 and 0 is 1, and in 12, the difference between 1 and 2 is also 1. Now consider another example with a smaller range, from 10 to 15. The output in this case is 10, 12, as those are the only stepping numbers within this range. Looking closer at the range from 10 to 15, the two stepping numbers are 10 and 12. For 10, the absolute difference between the digits 1 and 0 is exactly 1, making it a valid stepping number. Similarly, for 12, the difference between the digits 1 and 2 is 1, so it is also valid. The other numbers in this range 11, 13, 14, and 15 are not stepping numbers because the absolute difference between their digits is not 1. Now, in the third example, when the range is from 0 to 0, the output is simply 0. Since the range includes only one number and 0 is inherently a valid stepping number, it is directly included in the output. When solving this problem, there are several edge cases to consider. First, if low equals high, the output will include just one number, provided it is a valid stepping number. For instance, if both low and high are 0, the result will be 0. Another important edge case is when the range includes very large numbers, such as up to 10 to the power of 9. The solution must be efficient enough to handle such large ranges and compute all stepping numbers without running into performance issues. Additionally, when the range spans multiple digits, the algorithm must ensure that stepping numbers are generated correctly while maintaining computational efficiency. Handling these scenarios effectively will ensure the solution works for all possible inputs within the given constraints. To solve the stepping numbers problem, we first consider a brute force approach. The idea here is simple: iterate through every number within the range, low, high, and check whether each number qualifies as a stepping number. A number qualifies if the absolute difference between every two adjacent digits is exactly 1. While this method is straightforward and easy to understand, it becomes computationally expensive. For every number, we must check its digits individually, which leads to a time complexity of n*d, where n is the size of the range and d is the average number of digits per number. The space complexity is minimal, as we don't need additional data structures. However, for large ranges, this approach becomes inefficient because it doesn't optimize for the fact that most numbers in the range are not stepping numbers. Instead, we can consider an alternative approach, breadth-first search, or BFS. Here, stepping numbers are generated sequentially by starting with each digit from 0 to 9. From a given number, we append digits that differ by 1 from the last digit to generate the next potential stepping numbers. This eliminates the need to check non-stepping numbers, making the process significantly more efficient. Now, let's look at the BFS approach in more detail. We begin by initializing a queue with all single-digit numbers, from 0 to 9. Then, for each number dequeued, we examine its last digit and calculate the next possible digits by subtracting 1 and adding 1. For example, if the last digit is 3, we can append 2 or 4. These new numbers are added to the queue only if they fall within the range low, high. This process continues until the queue is empty, at which point we will have collected all valid stepping numbers. The time complexity of this approach is O, k, where k is the total number of stepping numbers in the range. The space complexity is also O, k, as we need to store the queue and the results. The BFS approach is highly efficient because it avoids unnecessary checks for non-stepping numbers. However, it does require additional memory to manage the queue. An alternative to BFS is depth-first search, or DFS, which uses recursion to generate stepping numbers. Like BFS, it starts from each digit and recursively appends valid digits to form new numbers, exploring each path fully before backtracking. In terms of performance, DFS has a similar time complexity of O, k, where k is the total number of stepping numbers, but its space complexity is O, d, where d is the maximum depth of recursion. This depth corresponds to the number of digits in the largest number within the range. While this results in slightly lower space usage compared to BFS, DFS comes with the risk of stack overflow for very large ranges, especially when the recursion depth becomes significant. On the other hand, BFS is better suited for generating all valid stepping numbers in a range because it avoids these recursion depth issues and processes numbers level by level. For this problem, BFS provides a balanced approach, combining efficiency and safety. By systematically exploring all valid numbers, it ensures orderly generation while avoiding the pitfalls of brute force or deep recursion. Additionally, BFS avoids iterating through non-stepping numbers, making it the most practical choice for larger ranges. When comparing the three approaches, the brute force method is clearly unsuitable for large ranges due to its inefficiency. DFS is a viable alternative but can lead to stack overflow in extreme cases where the range is large and the recursion depth becomes significant. BFS strikes the right balance between efficiency and safety, making it the optimal choice for this problem. By iteratively generating stepping numbers, BFS ensures that we only process valid candidates, staying within the given range, and avoids the computational overhead of brute force or the memory risks of DFS. Ultimately, the BFS strategy leverages the key observation that stepping numbers can only be formed by appending digits that differ by 1. Starting from each digit 0 to 9 ensures complete coverage of all possible stepping numbers, and the systematic, level-by-level exploration guarantees both correctness and efficiency. For this reason, BFS is the final strategy we recommend for solving the stepping numbers problem effectively. To solve the problem of identifying stepping numbers within a given range, we start by understanding the concept of a stepping number. A stepping number is one where the absolute difference between every two adjacent digits is exactly 1. For example, 12 and 21 are stepping numbers, but 13 is not because the difference between 1 and 3 is 2. The task is to identify all such numbers within the range low, high. To do this using the brute force approach, we begin by iterating through every number in this range, from low to high. For each number, we extract its digits one at a time and compare each digit with the next. If the absolute difference between any two adjacent digits is not equal to 1, we discard the number. However, if all adjacent digits meet this condition, we determine that the number is a stepping number. Once we identify a number as a stepping number, we store it in a list that holds all valid results. This list will ultimately contain all stepping numbers within the range. After iterating through the entire range, we return or print this list as the final output. Now, let's discuss some key insights about this approach. The digit-by-digit comparison to ensure the absolute difference between adjacent digits is 1 is the defining property of stepping numbers. While the brute force method is simple and straightforward, it is not optimized. The time complexity is O, n*d, where n is the number of integers in the range, low, high, and d is the average number of digits in each number. Additionally, we need to consider edge cases. For instance, single-digit numbers from 0 to 9 are always stepping numbers since there are no adjacent digits to compare. We must also ensure the range is valid, meaning low is less than or equal to high. Lastly, numbers with leading zeros should be treated as regular integers, for example, 0,1 is the same as 1. To implement this algorithm, we use a list as the primary data structure to store the resulting stepping numbers. Lists are ideal because they preserve the order of numbers and allow efficient appending of results. For example, when we explore the range 10, 21, we start by iterating through each number in this range 10, 11, 12, and so on, up to 21. For each number, we perform the stepping number check to decide whether to include it in our result list. This simple iteration through the range ensures that we evaluate every potential candidate for stepping number status. Let's delve into the detailed process of checking each number. Take the number 10 as an example. First, we extract its digits, 1 and 0. Then, we calculate the absolute difference between these digits, which is abs, 1 to 0, and find that it equals 1. Since this satisfies the stepping number condition, we add 10 to the result list. Next, consider the number 11. Its digits are 1 and 1, and the absolute difference is abs, 1 to 1, which is 0. This does not meet the condition, so 11 is not a stepping number. Similarly, for 12, the digits are 1 and 2, and abs, 1 to 2, equals 1, making it valid. We continue this process for all numbers in the range, adding valid stepping numbers like 21 to the result list. By the end, the final list of stepping numbers for this range is 10, 12, 21. The key operations in this algorithm include digit extraction and comparison. To extract the digits of a number, we repeatedly use integer division and modulo operations. For example, with the number 123, we find the last digit using 123% 10, which gives 3. Then, we reduce the number to 12 by performing 123 //10. Repeating this process, we extract 2 and then 1. This technique allows us to systematically obtain all digits of a number. For the comparison, we use the absolute difference between two digits, verifying that abs, d1 d2, equals 1. This ensures that the stepping number condition is satisfied for each pair of adjacent digits. Although the brute force approach works, it becomes inefficient for large ranges. To optimize, we can use methods like breadth-first search, BFS, or depth-first search, DFS, treating each number as a node in a graph. These approaches significantly reduce unnecessary checks by building stepping numbers incrementally. Additionally, we can implement early termination during the digit check process. If any pair of adjacent digits fails the stepping condition, we immediately stop checking the rest of the number. For edge case optimization, single-digit numbers can be directly added to the result list before initiating checks for numbers greater than or equal to 10. These optimizations help make the algorithm more efficient while maintaining accuracy. Here, we start by importing the D class from the collections module, which will help us efficiently implement a breadth-first search, or BFS, approach. Inside the count stepping numbers method, we initialize an empty list called result to store the stepping numbers that fall within the given range. We also create a queue using deque and populate it with the digits 0 through 9, as these are the potential starting points for our stepping numbers. Next, we enter a while loop that continues as long as there are elements in the queue. In each iteration, we use popleft to retrieve the first element from the queue. If this number exceeds the upper limit, high, we skip further processing for that number by using the continue statement. If, however, the number falls within the range defined by low and high, we append it to the result list. Now, we need to generate the next possible stepping numbers based on the current number. To avoid leading zeros, we only proceed if the number is greater than 0. We calculate the last digit of the current number using the modulus operator, and then check if we can append new numbers by either decrementing or incrementing this last digit. If the decrement digit is valid, we append a new number formed by multiplying the current number by 10 and adding the decrement digit. Similarly, if incrementing the last digit is valid, we append the resulting number to the queue. This way, we systematically explore all possible stepping numbers. Finally, after the BFS traversal is complete and we've gathered all the valid stepping numbers, we return the result. But before returning, we ensure the numbers are sorted, as stepping numbers may be added to the result list in an unordered manner during the BFS process. By calling Python's built-in sorted function on the result list, we guarantee that the output is in ascending order. This completes our implementation of the count stepping numbers method, which efficiently generates all stepping numbers within the specified range using a BFS approach. Here, we start with a Java implementation of the problem. The method count stepping numbers takes two integers, low and high, representing the range within which we need to find stepping numbers. We begin by initializing an empty list called result to store the stepping numbers and a queue to facilitate a breadth-first search approach. The queue is pre-populated with the digits 0 through 9, as these represent potential starting points for our stepping numbers. Next, we enter a loop that continues until the queue is empty. Inside the loop, we retrieve and remove the first number in the queue using poll. If this number is greater than high, we skip further processing for it since it exceeds our range. However, if the number falls within the range specified by low and high, we add it to the result list. Finally, we check if the number is greater than 0 to avoid generating additional numbers with leading zeros, and if so, we prepare to generate its next possible stepping numbers. To generate the next stepping numbers, we first calculate the last digit of the current number using the modulus operation. Based on this last digit, we determine which numbers can be appended to the current number to maintain the stepping property. If the last digit is greater than 0, it means we can safely append last digit 1 to the number, so we add it to the queue. Similarly, if the last digit is less than 9, we can append last digit plus 1, and this number is also added to the queue. By following this logic, we ensure that all valid stepping numbers are generated and explored. Once the queue is empty and all possible stepping numbers have been processed, we sort the result list to ensure the numbers are in ascending order, as required. Finally, we return the result list containing all stepping numbers within the specified range. To solve the stepping numbers problem, let's start with an example where the range is from 0 to 21. We begin by initializing an empty list called result to store our stepping numbers and a queue containing all single-digit numbers from 0 to 9. This queue acts as the starting point for generating stepping numbers. First, we process the number 0 by popping it from the queue. Since the number is 0, we skip generating any further numbers and directly add 0 to our result list. Next, we process the number 1. After adding 1 to result, we calculate its potential stepping numbers by appending its last digit minus 1 and last digit plus 1, resulting in the numbers 10 and 12, which are added to the queue. We repeat this process for numbers 2 through 9, adding each to result in generating their respective stepping numbers, like 21 and 23 for 2. At this stage, the queue is continuously updated with valid numbers for further processing. Now, we process the numbers 10 and 12 from the queue. For 10, we add it to result and attempt to generate its stepping numbers, which would be 101 and 121. However, both of these exceed the upper limit of 21, so we skip adding them to the queue. Next, we process 12, adding it to result as it falls within the range, but no new numbers are generated since they would also exceed the range. Finally, we sort the result list and return it, giving us the stepping numbers 0, 1, 2, 21. Now, let's consider a new example with a range from 10 to 15. Here, we initialize the result list and queue in the same way as before. When processing numbers 0 through 9, we skip all of them since they fall outside the range. For the number 10, we add it to result and attempt to generate its stepping numbers, 101 and 121, but both exceed the upper limit of 15 and are ignored. Next, we process the number 12. Since it falls within the range, we add it to the result list. However, no new stepping numbers are generated from 12, as they would exceed the upper limit of 15. With no more valid numbers to process, we sort the result list and return it, producing the final output, 10, 12. Let's now examine a third example where the range is from 100 to 300. Once again, we initialize an empty result list and a queue containing single-digit numbers from 0 to 9. This time, when processing these single-digit numbers, we skip all of them because they fall outside the specified range. Moving on, we process numbers like 101, 121, and 123, which are valid stepping numbers within the range. We add them to the result list and attempt to generate further stepping numbers from them. For instance, numbers like 1010 and 1012 would be generated from 101, but they are skipped as they exceed the upper limit of 300. Finally, after processing all valid numbers and skipping any that fall outside the range or exceed the upper limit, we sort the result list and return it. The final output for this example is 101, 121, 123. This demonstrates how our algorithm effectively identifies and generates stepping numbers within a given range by leveraging a breadth-first search approach while adhering to the constraints of the problem. To analyze the time complexity of our algorithm, we start with the initialization step. Here, the queue is populated with digits 0 through 9, which requires constant time, 1, since it involves adding only 10 fixed digits. Next, the breadth-first search traversal begins. For every number dequeued, we generate its valid stepping number children by appending either last_digit 1 or last_digit plus 1 to the current number. The number of nodes generated depends on the range specified by low and high and the number of digits in high. A number with d digits can generate at most 2*d stepping numbers. Since we explore all stepping numbers up to high, the BFS processes at most high numbers in the worst case. Finally, we sort the resulting list of stepping numbers. The size of this list, at most, equals the number of stepping numbers in the range low, high, which is bounded by high. Sorting this list takes k*log k, where k is the size of the result list, and in the worst case, k is high. The dominant factor in the time complexity is the BFS traversal, so the overall time complexity combines the traversal and the sorting steps. Specifically, this is high for BFS traversal and k*log k for sorting. Since k is at most equal to high, the total complexity simplifies to high plus high*log high. This can further be expressed as high*log high, which represents the worst-case scenario. This breakdown highlights the efficiency of our approach, as it directly focuses on generating valid stepping numbers rather than processing every number in the range. Now, let's examine the space complexity. During the BFS traversal, we use a queue to store intermediate numbers. The maximum size of the queue occurs when all valid stepping numbers of a given length are enqueued before processing. In the worst case, the queue can store up to high numbers. Additionally, the result list stores all valid stepping numbers in the range low, high. The size of this list is proportional to the total number of integers in the range, which means it also requires high space. Lastly, the auxiliary space used for variables like last_digit in number is negligible, contributing only 1 space. Therefore, the total space complexity is dominated by the queue and result storage, leading to an overall complexity of high. To better understand the efficiency of BFS, let's compare it with the brute force approach. A naive solution would iterate through all numbers in the range low, high, and check for each number if it is a stepping number by examining its digits. This involves iterating through high, low numbers and checking each one, which takes d time, where d is the number of digits in the number. Therefore, the time complexity of the brute force approach is high, low, *d. In contrast, BFS avoids examining non-stepping numbers by directly generating only valid stepping numbers. This makes BFS significantly more efficient, with a time complexity of high*log high compared to high, low *d for brute force. Additionally, BFS reduces space usage since it does not need to store all numbers in the range low, high, further highlighting its advantage over the brute force method. Finally, let's analyze the best and worst case scenarios for our BFS approach. In the best case, when low and high are small, BFS processes fewer numbers, and the sorting step becomes negligible. The complexity in this case simplifies to high. In the worst case, where high is large, BFS processes a significant number of numbers, and the sorting step becomes more impactful, resulting in a complexity of high*log high. To justify this mathematically, we note that BFS explores stepping numbers in a tree-like structure. Each node generates at most 2 children, and the depth of this tree is bounded by the number of digits in high, which grows logarithmically with the value of high. Sorting is efficient due to the relatively small size of the result list compared to high. In conclusion, the BFS-based solution is far more efficient than brute force, especially for large ranges, and it balances both time and space complexity effectively to handle the problem with optimal performance. When working with stepping numbers, there are a few common mistakes to watch out for. First, it's easy to misunderstand the rule for digit transitions. A stepping number requires that the absolute difference between every pair of consecutive digits is exactly 1. For example, 12 is valid because 2 is 1 away from 1, but 135 is not valid since 3 and 5 differ by more than 1. Missing such transitions can lead to incorrect results. Another frequent issue is inefficient iteration. Instead of leveraging properties of stepping numbers, some solutions brute force through all numbers in a range, even those that have no chance of being valid. This can significantly slow down the solution, especially for large ranges like 10,000 to 1 million. Lastly, boundary conditions are often mishandled. Single-digit numbers, like 0 through 9, are always valid stepping numbers. If these aren't handled explicitly, a solution might exclude or misclassify them, leading to incomplete or inaccurate results. Another mistake to avoid involves handling numbers with leading zeros. For example, treating 012 as a valid stepping number is problematic because leading zeros aren't allowed in standard integer representations. This assumption can lead to invalid inputs or errors in processing. Additionally, incorrect implementation of BFS or DFS is a common pitfall. When generating stepping numbers dynamically, invalid digits may be added to the sequence. For instance, appending a digit out of bounds, like -1 or 10, during traversal can lead to redundant calculations or incorrect results. Ensuring that every added digit satisfies the stepping condition and stays within bounds is critical for producing accurate and efficient solutions. From an interview perspective, stepping numbers provide an excellent opportunity to demonstrate problem-solving skills. Recognizing that they can be efficiently generated using BFS or DFS is key. By starting with digits 0 through 9, valid next digits can be appended dynamically based on the stepping condition, eliminating the need to iterate through the entire range. This approach is far more efficient than brute force, which typically cannot handle the constraints of an interview setting. It's also important to test edge cases, such as ranges that only include single-digit numbers, very large ranges with no stepping numbers at all, or ranges that include boundary values. Finally, understanding related problems can provide additional context. For example, sequential digits, letter case permutation, permutations, and combinations all involve similar techniques, so familiarity with these can help you identify patterns and apply efficient solutions. When exploring alternative approaches to solve the stepping numbers problem, the brute force method is often the first that comes to mind. This involves iterating through all numbers in the range and checking each one digit by digit to verify if it satisfies the stepping condition. While simple to implement, it becomes inefficient for large ranges due to its O and *d complexity, where d is the number of digits in a number. A more efficient approach is using BFS or DFS to generate stepping numbers dynamically. Starting from single digits, valid next digits are appended based on the stepping condition, allowing the algorithm to avoid iterating through invalid numbers. This approach reduces complexity and is better suited for larger ranges, though it requires careful implementation to avoid errors. Finally, mathematical recursion offers a compact and elegant alternative. By defining constraints on the current digit and range, recursion can generate stepping numbers directly. However, this approach requires precise handling of base cases and recursion depth to ensure correctness and prevent stack overflow. Great job! We've reached the end of our solution to the stepping numbers problem. To recap, we discussed the brute force approach and highlighted important insights about digit-based constraints. Remember to always weigh the efficiency of your approaches and keep practicing. Thanks again for joining, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!